In this video, we're looking at some fundamental guidelines that play a crucial role in software engineering. These aren't just any rules, they're the best practices that help developers make informed decisions throughout the software development lifecycle, tackling common challenges such as complexity, scalability, and teamwork. When you're building software, the landscape is complex and ever-changing. Here's where our principles come into play. They ensure our software isn't just built, but is also predictable, reliable, and adaptable. Whether it's reducing errors, boosting team productivity, or making the software easier to maintain and extend, these principles help us manage the many moving parts of software development smoothly. At the heart of object-oriented design, we find the solid principles. They're all about crafting software that's easy to understand, extend, and modify, all while keeping bugs at bay. These principles guide us in creating a system where everything has its place and purpose, reducing unnecessary dependencies and making our code clean and modular. The single responsibility principle is all about focus. Each class should have one job and one job only. This way, when changes come along, there's a clear line of responsibility, making our code less fragile and much easier to manage. Let's take the example of an invoice class with multiple responsibilities. Not only is it generating invoices, but it's also taking care of sending them out via email. Now, at first glance, this might seem efficient. Kill two birds with one stone, right? Well, not quite. Here's why mixing these two responsibilities can lead to headaches down the road. Firstly, the invoice class is overworked. It's tasked with both creating the invoice and managing the email dispatch. These responsibilities are inherently distinct. Generating an invoice and sending an email are two different domains of functionality and ideally should be handled separately. Let's say you decide to change how emails are sent. Perhaps you want to add some logging for email dispatches or switch to a different email service provider. You'd have to dive into the invoice class and tinker with the email-related code. But here's the catch. These changes could disrupt the invoice generation part of the code that was working perfectly fine. This intermingling of code for different functionalities makes your codebase fragile and susceptible to bugs whenever modifications are made. Moreover, think about the testing nightmare this setup could create. If you want to test just the invoice generation logic, you still have to configure email sending, which complicates the testing environment unnecessarily. You end up spending more time setting up tests that cover more ground than necessary. By applying the single responsibility principle, we can separate the concerns. We will create two separate classes, one for generating the invoice and another for sending the email. Now when you need to generate an invoice and send an email, you can do so by calling both classes. First, we've got the invoice generator class. Its only job? Generating invoices. Then there's the email sender class, tasked solely with sending out those emails. This is a perfect example of the separation of concerns principle in action. Each class sticks to its own business. What's great about this setup is that each piece of functionality gets the focus it deserves without any unnecessary overlap. With our classes neatly divided, maintenance becomes easy. Need to update how invoices are formatted? Tweak the invoice generator class. Want to switch email providers? You adjust the email sender class. Since each class operates independently, making changes to one doesn't compromise the other. Testing, often a thorn in our side, just got a whole lot smoother too. With each class handling its own business, we can test them separately. This means we can run unit tests on the invoice generator without even thinking about the email side of things. And if something fails, you know exactly where the problem lies. No more combing through tangled code trying to pinpoint the issue. Sticking to the single responsibility principle not only tidies up your code but also streamlines your entire development process. By keeping each class focused on a single task, we minimize the risk of bugs during updates, enhance the clarity of our system, and boost our code's modularity. In simpler terms, adhering to the single responsibility principle leads to code that's cleaner, more maintainable, and easier to test. You can think of the open-closed principle like architecture. Once you've built a house, you don't reshape it, you just add more to it. Our software should be open to extensions without needing to modify the existing code. Let's say you have an invoice printer class that prints invoices for customers in plain text. Later, a new requirement comes in to add support for printing invoices in PDF format. Without following the open-closed principle, you might be tempted to modify the invoice printer class directly to accommodate the new format, which would violate the open-closed principle because the class would now need to be modified every time a new format is added. Messing about with the existing method doesn't just complicate things, it makes the whole system fragile. The more we fiddle with it, the higher the risk of messing up something that was working perfectly fine before. Then there's the issue of scalability. As we keep adding more formats, this method's going to get increasingly convoluted and challenging to manage. It's like stuffing more clothes into an already bursting suitcase. Eventually, it's going to be impossible to close. So, in a nutshell, this approach of constantly modifying the invoice printer class is not just a bit of a hassle, it fundamentally goes against the principles of good sustainable software design. We're better off finding a way to extend functionality without having to meddle with the existing codebase every time a new requirement pops up. The new version is now open for extension, so we can introduce new formats, say HTML or XML, by simply crafting new subclasses like HTML invoice printer that play nicely with our invoice printer interface. This neat trick lets us expand what our software can do without fiddling with the existing, smoothly running code. The core invoice printer class remains untouched, no matter the updates. It's a solid rock in our coding landscape. Because we're not tweaking it every time we add something new, we drastically cut down the risk of bugs sneaking into our stable setups. The new design is inherently more scalable. As our needs grow, we can seamlessly tack on new printer classes to handle different formats. It's a bit like having building blocks that you can add to without having to rebuild the whole structure from scratch. And let's talk about clean code. Our code is now more modular and far easier to test. It lines up with the best design practices, making it simpler for anyone in the team to understand and work with it. Using abstractions like interfaces or abstract classes, we keep the core essence of our logic untouched, yet flexible enough to welcome new functionalities. By embracing the open-closed principle, or OCP, we're not just tinkering for the better, we're setting ourselves up for a future where our software can evolve without disruption. This approach significantly boosts maintainability and stability across the board. The Liskov substitution principle is about trust in relationships, specifically between a parent class and its children. Any child class should be able to stand in for a parent class without causing a meltdown. Let's say we have a base class bird with a method fly. In our setup, all birds are expected to fly, but that is not always true in the real world. Take penguins, for instance. When our penguin class tries to use the fly method, it ends up throwing an exception because, well, penguins can't fly. This situation causes a bit of a mess because it breaks the expectation set by our bird class that all birds should be able to fly. Here's where things get tricky. Any piece of code that's designed to interact with a bird object and expects it to fly will hit a snag when it runs into a penguin. This goes against the whole idea of substitutability, where we expect a child class to seamlessly step into the shoes of its parent class without causing upheaval. As a result, developers now find themselves having to add checks all over the place to handle cases where a bird can't fly, making the code more complex and, frankly, a bit of a headache to maintain. To fix this, we can refactor with the Liskov substitution principle in mind to smooth things out. The goal here is to avoid forcing all birds to pretend they can fly. We can smarten up our design by introducing a new interface, iFlyable, specifically for birds that can fly. This interface will house the fly method. Then, we remove the fly method from our base bird class. This way, we're decoupling the ability to fly from being a general bird behavior. Birds that fly, like sparrows and eagles, will implement the iFlyable interface, and birds that don't, like our friend the penguin, won't have to deal with flying at all. By making this change, we align our software design more closely with reality and ensure that each subclass under bird only takes on behaviors that make sense for that particular bird. This not only simplifies our code by removing unnecessary checks, but also keeps it robust and easier to manage. This way, we maintain the integrity of our bird hierarchy without any forced assumptions, making our code cleaner and more logical. The introduction of that iFlyable adjustment has several benefits. It is now implemented only by birds that truly can fly. This change maintains the integrity of our substitutability. Any flying creature can replace another without breaking functionality, staying true to the expectations set by our system. The introduction of iFlyable has also expanded the flexibility of our design. It is no longer exclusive to birds. Any flying animal, be it a bat or an insect, can implement this interface. This adaptability doesn't compromise the core behaviors encapsulated in the bird class, enhancing the system's overall design coherence. Moreover, our code has become significantly cleaner and easier to manage. We've eliminated the need for cumbersome conditional logic or complex error handling related to flying capabilities. It's now straightforward. If an animal implements iFlyable, it flies. If not, it doesn't. This clarity simplifies testing and maintenance, reducing the likelihood of bugs. Adhering to the Liskov substitution principle not only prevents errors and enhances system stability but also promotes a modular and flexible code architecture. By ensuring that our classes accurately represent real-world behaviors without imposing unnecessary expectations, we create a robust, scalable system that's easier to extend and maintain. This approach showcases how professional software engineering principles can lead to practical, efficient solutions in system design. No one likes being overloaded with tasks they don't need. The interface segregation principle helps us keep our interfaces lean, giving classes only the methods they need to do their jobs. Let's discuss a scenario that highlights a common design challenge and how we can solve it effectively. Imagine we have an iWorker interface designed to cater to both manual and automated workers. This interface includes methods for tasks like taking breaks, which are specific to human workers, and performing automation tasks, which apply to robots. However, both our human worker and robot worker classes are required to implement this one-size-fits-all interface. This design approach violates the interface segregation principle. Our human worker class ends up with automation methods that are completely irrelevant, while our robot worker might be saddled with human-specific tasks like taking breaks. This not only leads to unnecessary and confusing code but also forces both classes to handle exceptions or irrelevant methods. Furthermore, this fat interface binds unrelated functionalities together, complicating the extension or modification of the system without affecting all types of workers. Essentially, any modification to the interface impacts both human and robot workers, even if the change is relevant to only one type. To streamline this, we need to refactor our approach by breaking down the iWorker interface into smaller, more focused interfaces, each aligning with specific worker responsibilities. For example, we could create an iRestable interface for break-taking methods and an iAutomatable interface for automation tasks. This way, human worker would implement iRestable, and robot worker would implement iAutomatable. By doing so, each worker class implements only the interfaces pertinent to its functionality. The benefits of this refactoring are significant and bring much-needed clarity and simplicity to our system. By creating focused interfaces, we ensure that each interface includes only methods relevant to a specific functionality. This change means that our human worker class no longer needs to deal with automation tasks, and our robot worker isn't burdened with break-related methods that don't apply to it. Furthermore, this refactoring decouples the responsibilities that were previously intertwined. Now, each type of worker is linked only to the functionalities that are relevant to them. This clear delineation of responsibilities prevents the overlap of unrelated duties and keeps each class clean and focused on its intended purpose. Moreover, the separation enhances the flexibility of our system. Changes or additions to one interface do not impact unrelated workers. For example, if we decide to expand automation capabilities, this development will not affect the human workers. This ensures that enhancements to one part of the system don't inadvertently complicate or break the functionality of another, maintaining a harmonious and efficient workflow throughout our codebase. Adhering to the interface segregation principle not only clarifies the roles and capabilities of each worker type but also enhances the system's modularity and maintainability. This method promotes a more scalable and adaptable codebase, ensuring that future changes are localized and do not unnecessarily complicate other parts of the system. The dependency inversion principle is about not getting too attached. High-level modules shouldn't be overly dependent on low-level modules. Instead, they should interact through abstractions. This keeps our system flexible and interchangeable. Let's talk through a common scenario in software development that sheds light on a crucial design principle. Imagine we have a user service class that's directly tied to a MySQL database class to manage user data. This setup is a classic example of tight coupling, where the high-level user service is entirely dependent on the low-level MySQL database implementation. This dependence is problematic because it locks us into using MySQL and makes it tricky to switch databases or even test the user service independently. For instance, if we decide to switch from MySQL to MongoDB, or perhaps to a file-based system, we would need to rewrite parts of our user service to accommodate the new database technology. This is not only inconvenient but also against the principles of good software architecture, specifically violating the dependency inversion principle. Furthermore, testing becomes a headache because the user service can't easily be isolated without involving MySQL database. This complicates unit tests and increases the risk of defects slipping through. The solution here involves embracing the dependency inversion principle by introducing a level of abstraction. We can create an iDatabase interface, which can be implemented by any database class, such as MySQL database, MongoDB database, or any other data storage mechanism. The user service then interacts with this iDatabase interface instead of a concrete database class. This shift decouples the user service from specific database implementations, allowing changes in data storage strategies without any modifications to the user service itself. For example, if you decide to switch to using MongoDB, you simply need to pass an instance of MongoDB database when setting up the user service. This method of dependency injection not only streamlines the transition between different databases but also significantly enhances the flexibility and scalability of our application. Testing the user service has also become much simpler. By injecting mock implementations of the iDatabase during testing, which don't rely on actual database connections, we significantly improve the testability of the service. This allows for more robust and isolated tests that help ensure our service is functioning correctly without the need for a live database. Finally, the overall scalability of our system benefits greatly from this architecture. Since introducing new storage mechanisms or modifying existing ones doesn't interfere with the higher-level user service, our system can grow and evolve with minimal disruption. This scalability ensures that our system can adapt to future needs with ease, further securing its long-term viability. In summary, adhering to the dependency inversion principle not only mitigates issues of tight coupling and inflexibility but also enhances the maintainability and scalability of the system. By relying on abstractions rather than concrete implementations, our software architecture remains robust, adaptable, and easier to manage as it evolves. While Solid gives us a strong foundation, there are other principles that also guide our coding journey, like dry, don't repeat yourself, KISS, keep it simple stupid, YAGNI, you aren't gonna need it, and the Law of Demeter. Each one encourages practices that avoid overcomplication, promote maintainability, and ensure that our software can grow and adapt over time. Drying pushes us to consolidate repeating logic into a single part of our system, which simplifies maintenance and minimizes the chance of bugs. Imagine you're working on a software program that calculates discounts for various types of customers, such as regular and premium customers. You've noticed that the same logic for calculating discounts is being used over and over again in different parts of your code. This is a classic case of code duplication, which can lead to several problems down the line. Firstly, having repeated code means that any time you need to change how discounts are calculated, you have to make the same update in multiple places. Not only does this increase the chances of missing an update, but it can also lead to errors and inconsistencies. Moreover, as your business grows and you add more customer types with their own discount rates, the issue of duplication will only get worse. This makes the system harder to maintain and less scalable. The solution to this problem lies in adhering to the drying principle. By refactoring the code, you can extract the common discount calculation logic into a single method. This method would then accept parameters specific to each customer type, making the code reusable and significantly reducing duplication. The benefits of such refactoring are substantial. By centralizing the discount calculation logic into one method, you eliminate repetitive code, making the entire system easier to manage. Whenever the discount rules change, you only need to update this one method. This ensures that the changes are consistent across all customer types without the risk of discrepancies. Additionally, the system becomes more scalable because adding new customer types or changing discount rates simply involves passing new parameters to the existing method, rather than duplicating more code. By embracing the dry principle, you not only streamline your code but also reduce the complexity and potential for bugs. It promotes more efficient development practices by centralizing and reusing logic, making your code easier to maintain, extend, and manage as your business evolves. This approach isn't just about keeping the code base neat, it's about enhancing the robustness and adaptability of your system. KISS targets the simplest solution that works, which often turns out to be the best solution. Imagine you're given the straightforward task of calculating the sum of numbers in a list. It's tempting, especially for the enthusiastic developer, to dive into creating layers of abstraction like an ISUM calculator interface or a sum calculator class. However, this approach can unnecessarily complicate what should be a simple task. In this scenario, introducing such abstractions doesn't really add value. It only adds complexity and can lead to over-engineering. The problem is that these layers, while perhaps intellectually satisfying, make the task more complicated than it needs to be. Plus, if this code is part of a larger system, it becomes even more of a headache. Other developers, or even you in the future, will have to navigate these unnecessary complexities, making the code much harder to maintain. The solution? Embrace the KISS principle. By stripping away the unnecessary abstractions, we return to the essence of the problem and address it directly. Refactoring the code to remove these layers and simplify the solution brings several benefits. The code becomes simpler, directly addressing the problem without any detours through unnecessary abstractions. It's clean, clear, and easy to understand. With the solution being so straightforward, future maintenance and modifications become much simpler. There's less that can go wrong, and adjustments can be made quickly without sifting through complex layers. Additionally, eliminating the need for interfaces or additional classes to perform a basic sum greatly reduces both the cognitive load on developers and the resource overhead on the system. Following the KISS principle not only helps in keeping the code base efficient and manageable but also ensures that the solutions are as intuitive and bug-resistant as possible. By focusing on simplicity, we avoid over-engineering and create software that's easier to maintain and extend. It's a reminder that sometimes, the best solution is the simplest one that fully satisfies the requirements without adding unnecessary complexity. YAGNI warns us against adding features until they are actually needed, which keeps our projects lean and efficient. Imagine a developer, tasked with creating a user authentication system for an application. The only requirement initially is to allow users to log in using a username and password. However, thinking ahead, the developer decides to also implement support for OAuth, like Google and Facebook logins, multi-factor authentication, and even considers biometric login capabilities. While forward thinking can be valuable, in this case, it introduces several challenges. The complexity also increases the maintenance burden significantly. Future developers, or even the original developer revisiting the project later, will have to wade through and maintain this additional, potentially unused code, which increases technical debt. The solution here lies in embracing the YAGNI principle. In this scenario, the developer should focus solely on creating a robust username and password authentication system. Other authentication methods can be added later, if and when they become necessary. By refactoring the code to remove these premature features, the benefits are immediate and significant. The code becomes simpler and more focused, directly addressing the current needs without the clutter of unnecessary functionality. This simplification not only saves time and resources but also enhances the clarity and maintainability of the code. Additionally, when or if the time comes to integrate OAuth or other methods, they can be incorporated incrementally, based on actual requirements, allowing for a more manageable expansion. Adopting the YAGNI principle reduces unnecessary complexity and technical debt, improves code maintainability, and is more efficient, developing only what is needed at the moment. This focus prevents over-engineering and ensures that development efforts are directly aligned with user needs. The Law of Demeter suggests that objects should know as little as possible about each other, promoting loose coupling and greater modularity. Let's imagine an online retailer that needs to send goods to customers, a process that involves classes representing customers, their addresses, and orders. These classes are quite straightforward and commonly used in the business logic. A specific part of this process involves the printing of a shipping label, which one might initially think should be part of the order class. However, there's a subtle issue in this design. Within the order class, the method, print shipping label, directly accesses the address object through the customer object. This results in a message chain like customer.address.street, which is a classic example of violating the Law of Demeter. Essentially, the Law of Demeter suggests that an object should not know too much about the internal structure of other objects it interacts with. This kind of design leads to tight coupling, meaning any changes in the customer or address classes would necessitate changes in the order class as well, impacting the maintainability and flexibility of the system. To resolve this and adhere to the Law of Demeter, we should rethink how the order class interacts with customer and address. Rather than having the order class delve into the details of the customer to get to the address, we can encapsulate this behavior within the customer class itself. By shifting the responsibility for retrieving the shipping address into the customer class, the order class needs only to interact with a single method on customer, let's call it getShippingAddress. This method would handle all the details internally, shielding the order class from any changes to how addresses are stored or managed. This refactoring brings about several improvements. The interaction between the order class and the customer class is now through a clear, well-defined interface, getShippingAddress. This approach significantly reduces the dependencies the order class has on the internal structure of the customer or address, enhancing the flexibility of the codebase. By doing this, we've encapsulated the details of the address class within the customer. The order class doesn't need to know the specifics of where or how the address is stored, it simply asks the customer for the shipping address. This encapsulation effectively hides the complexity of the address class from the order class. Moreover, the maintainability of the system is greatly improved. If the format or structure of the address needs to change, perhaps to include a new field like a country or postcode, those changes can be confined to the customer class. The order class remains unaffected by these adjustments, which simplifies ongoing maintenance. By implementing the Law of Demeter, we ensure that our classes remain modular and are not overly reliant on the internal structures of other objects. To wrap up, we've explored some of the fundamental principles that form the backbone of software engineering: solid, dry, KISS, YAGNI, and the Law of Demeter. These principles aren't just theoretical concepts. They are practical guidelines that help us write code that is clean, maintainable, and scalable. By adhering to these principles, you can reduce complexity, avoid duplication, and create systems that are easier to extend and debug. Remember, good software engineering isn't just about solving problems. It's about solving them in ways that stand the test of time. Apply these principles thoughtfully, and they'll become the foundation of your growth as a software engineer.